Hello, ladies and gentlemen. My name is Metin Tolan. I'm professor for physics at TU Dortmund University, Technische Universität Dortmund, and the major field of my working group in Dortmund is the investigation of soft matter materials with synchrotron radiation, such as proteins and other building blocks of life, how they behave under extreme conditions. This is a very exciting topic, but I'm not going to talk about this topic today. I'm going to talk about one of my favorite hobbies, and one of my favorite hobbies is James Bond. So the title of the talk today is Shaken, Not Stirred, James Bond in the Spotlight of Physics. Of course, it's a physics talk because I'm a physicist, and we will discuss the physics in the James Bond movies. In order to do this, you'll find here the outline of my talk. It will start with a short introduction. So I just would like to explain to you who James Bond is. And then we go deep into the matter. We will discuss about chases and escapes. We will discuss in very great detail how one watch of James Bond is functioning. And I will discuss with you a mirror image, which is from a James Bond movie. And at the end of the talk, we will discuss the title of the talk, Shaken, Not Stirred. You may all know that James Bond is drinking his vodka martinis, shaken, not stirred, and there is a very good physics reason why he is doing this, and we will come to this at the end of the talk. So let's start with the introduction. Of course, James Bond was also stopped by the coronavirus pandemic. On the 5th of March, it was announced that the movie, which was scheduled for the 2nd of April, will be postponed to November 2020. So will be postponed for 6 months. There you could already see that the corona pandemic will be very, very serious, and the makers of the James Bond movie, they also already knew this at that time. So James Bond was invented by Ian Fleming, a British novel writer who died too early and who wrote in the year 1953 the book Casino Royale. It was a book about a spy who was working between the two superpowers, US and Soviet Union at that time, and this book became very popular, and the spy became very popular. So he wrote many more books about this spy, and they were all very successful. And it's not a matter of fact these days. It was also at the old days that successful books went to the cinemas. So James Bond was also going to the cinemas, and James Bond will now introduce himself by the 6 actors who played him so far when they are speaking the famous lines.
James Bond. Mein Name ist Bond. James Bond.
My name is Bond.
James Bond.
Who are you?
Bond, James Bond.
Thank you, mister.
My name's Bond. James Bond.
The name's Bond. James Bond.
I'm sure that you all know this, and you probably also know who James Bond is. James Bond was an ornithologist from Philadelphia. And this is really the true story, because Ian Fleming, he was the owner of very many books in his shelf, and one of the books was this book by the ornithologist James Bond. And he really took the name of the ornithologist and gave it to his spy. This is really the real story. And if you know this background, then you can really get the more deeper meaning of the following small clip from the 20s Bond movie Die Another Day.
What about you?
Oh, I'm just here for the birds.
Ornithologist.
See? So you already learned something. When you watch this movie the next time, you can say, well, in this small clip, it is referred to the origin of the name James Bond. Okay, so the profile of James Bond was, of course, defined by Ian Fleming, and I think his most striking thing is his 00 number. What this means is best introduced by his boss.
If you carry a 00 number, it means you're licensed to kill, not get killed.
It's a license to kill, not get killed. When you look in his passport, surprisingly, you find the following. His birthplace is Wattenscheid in Germany. So he's born approximately 15 kilometers from here, in Wattenscheid in the Ruhr area in Germany. This is surprising, but it is true. There is an official biography of James Bond, which is interesting by its own, but there is an official biography of James Bond. And in this biography, it has been defined that James Bond was born November 11th, 1920 in Wattenscheid. So he is almost 100 years old. For this age, he is in pretty good shape, I would say. He is the son of a Scottish engineer and a Swiss mountaineer. And the engineer, he just had to do something in the Ruhr area in Germany, and during that time, James Bond was born. This is the official story. Okay, then he has other properties, weapons, he has strengths, of course, he has weaknesses, alcohol, as we will see, and also women. Well, I will show you a small clip from the movie Goldfinger. You must bear in mind that this movie was shot in the year 1964. Nowadays, you can never show such a clip.
Just here.
No, a little lower down. I thought I'd find you in good hands.
Felix! Felix, how are you? Denk, meet Felix Leiter.
Hello.
Felix, say hello to Denk.
Hi, Nick.
Denk, say goodbye to Felix. Man talk.
1964. 1964. Okay. Then he speaks different languages, of course, German, as you know, he was born in Germany. He has some characteristics, and what is also important is that he has a mass of 76 kilograms and a size of 1.83 meters. This was defined by Ian Fleming, and the actors are very close to these numbers. For instance, Daniel Craig has a weight of 78 kilograms and 1.82 centimeters size. So I would say this is within the margin of error. Daniel Craig is the actual James Bond. And this was the first teaser for the movie No Time to Die, which was scheduled for April 2020 at that time. Okay, so let's start with the physics. We will discuss now one chase of James Bond. It is from the movie The Man with the Golden Gun of the year 1974. It was the second movie with Roger Moore as James Bond, and he was after Scaramanga, which is the villain in this Bond movie. But Scaramanga is with his car on the other side of a river, and James Bond is after him, but he cannot go over the river because there is no bridge. And take a look how he solved the situation.
Here's the bridge. It's 2 miles back. God damn! What's the hand doing now?
now, boy. The bridge is that way. You're not thinking that.
I sure am, boy. Ever heard of Evel Knievel?
I've never done that before.
Neither have I, actually.
Wow, interesting. So what did we see? So we want to understand what we have seen. Obviously, James Bond is driving with an AMC Hornet car, a car like this, here to this ramp of this bridge, which is broken. And then this ramp, since this ramp is a little bit twisted, the car spins along the longitudinal axis and lands on the other side at this ramp of the broken bridge. And we would like to understand this. So what is interesting on this? In physics, you, in general, must define an interesting question. Of course, you have to solve this question also, but very often it is really difficult to find an interesting question. What could be an interesting question here? Of course, as a physicist, you could calculate the flight path of the car. This is not that interesting, I can tell you. It's just a parabola. You may have learned this already in school. You can see here the blue curve was calculated with the exact parameters, and the red curve is calculated without the spinning on the around the longitudinal axis. So you can see the spinning around the axis does not affect the flight path of the car very much. What is really interesting is, of course, when you would like to land on the tires, this could be a little bit more difficult, but this is not an interesting question. An interesting question is the following. Suppose that this is really working. This would mean the following. These ramps are at a certain distance. We have a certain launching angle here. We have a certain twisting angle. All this is given. So if this stunt really works, then it could only depend on the initial speed of the car, which the car has when he is driving to the ramp. This means, in other words, if you know this speed of the car, then you can do this stunt. And this means if I give you the speed of the car, then you can do this stunt with your own car. Everybody can do it. Is this really true? Can really everybody do this stunt? Can you take your car and do the stunt when I give you the correct speed with which you have to enter the ramp? Provided you trust me, and I guess you trust me. So this is an interesting question. Can everybody do this? Provided this was a real stunt.
Are you the chap who designed or did the car stunt in the Houston Astrodome?
Yes, obviously this was a real stunt. So we are talking about something which is really working. This makes it even more interesting, I would say. Again, the question, can everybody do this with his own car? Can you do this with your own car? The answer is no, because we have to talk about spinning objects, about objects who are spinning around a certain axis. Rotations are only stable around certain axes, so-called symmetry axis. So for this body, these are the symmetry axis, and only rotations are stable when a body is rotating around an axis with a symmetric mass distribution around this axis. These are these three axes, but not this axis. I can show this to you with a small experiment. Let me take such a body, a book for instance, this book here, and if I rotate the book around the axis B, this is the axis which is going here through the middle, then the book is rotating stable. You see? The rotation of the book is quite stable. If I rotate the book around diagonal axis, the axis D, which is here, in this way, then you will see that the body is starting to stagger, and then the rotation is absolutely unstable. We can do the experiment a little bit more smart, but first I will explain to you what the makers of the stunt were saying, why the stunt was working.
On a computer.
The computer was used by the National Highway Safety Bureau in the investigation and reconstruction of single vehicle automobile accidents worldwide. The firm that happened to do that was a company in Buffalo, division of Cornell University. An ingenious engineer there by the name of Raymond McHenry visualized that we could do a complete football spiral type with a full-size automobile.
The exercise is quite complicated because the car has to be perfectly balanced. The steering wheel is in the middle.
The car would have been cut in half, widened about 2 inches. Everything was then centralized and balanced.
Aha, you have heard this. 2 things must be fulfilled so that this stunt can be done. Number 1 is you need a genius engineer to calculate all this. Well, for this, I can just tell you, when I'm giving the physics lecture for our beginning engineers in the first semester, the physics lecture, we are completely calculating this stunt there, from which you can see that we are only educating brilliant engineers here at TU Dortmund University. Well, the true story is it's not that complicated. Of course, you must know a little bit from physics, but then you can calculate this. So this is always exaggerated in movies. In movies, people are always saying, well, everything is tremendously complicated. It's not so complicated to calculate this. The second thing they mentioned, this was important. They need a car which was prepared in a very special way. The mass distribution around the longitudinal axis of the car must be as symmetrical as possible. So they cut the car in the middle, they put the steering wheel in the middle, they put the driver in the middle, they put the motor exactly in the middle, they put the trunk exactly in the middle, they took off the roof and replaced it by a very light one, so that they have a symmetric mass distribution around the longitudinal axis. Why did they do this? I can show this to you with a small experiment. This is a gyroscope, and this gyroscope can spin around this axis. So this axis would be the longitudinal axis of our car. And what we are now doing is the following. We have 4 masses which are placed around the rotation axis. Number 1 is here, number 2 is here on the front side, and on the back side, number 1 is here and number 2 is here. So this means that around the rotation axis, we have a totally symmetric mass distribution. So we have here 2 heavy masses, here 2 heavy masses. Around the rotation axis, the mass distribution is symmetric. And you will find this, this gyroscope spinning on the left side of the screen. Then we do the same experiment, but now the masses are distributed as follows. We have on the front side here the masses at these locations, and at the same locations on the back side, so that around the rotation axis the masses are distributed not in an equal manner. Heavy mass, no mass, heavy mass, no mass. You will see the rotation of this gyroscope on the right side of the screen. Take a look. Look carefully so that you can see the difference of the movement of the 2 gyroscopes. First, of course, the gyroscopes are spinning. This is not a big deal. But then I make a very small hit. You see a very small disturbance. Aha. You see? This gyroscope with the equal mass distribution, with the symmetric mass distribution, rotates totally stable. And the gyroscope with the non-equal mass distribution, with the non-symmetric mass distribution, rotates totally chaotically. So it became totally unstable. It's a very unstable rotation. And this would also happen with the car when the mass distribution is not stable, is not symmetrical. So this was the clue of this stunt. You needed a car with a total, with a symmetric mass distribution. This was the clue. The clue was a car. You need this prepared car. So you have to do some welding work on your car if you want to do this stunt. But then if you have such a car, you just have to measure the angle of the ramp, the length of the ramp. You have to measure the twisting angle of the ramp. And then obviously James Bond was also very carefully measuring this. And then of course you can drive over the ramp. You have to do some mathematics, and then you can calculate the speed with which you have to enter the ramp. And if you do this, the result is you have to enter the ramp with 64 kilometers per hour, and the tolerance is plus minus 3 kilometers per hour. This is doable. This is doable. This can be done by a stuntman. So in order to do this stunt, you need a prepared AMC Hornet car. You have to drive to this point with 64 kilometers per hour plus minus 3. And what do you have to do then? Nothing. The rest is done by physics. You also should not do anything inside the car. You should not really do some movement inside the car. And this was the reason why the stuntman was really fixed in the car. He was lying in the car and fixed by belts so that he can't move. And with this precautions, it was even possible to do this stunt in the first time. So you see there was a lot of physics involved in this kind of stunts, which you can find in James Bond movies. Okay, let's go to the next topic, to the watches of James Bond. The watches of James Bond always contain a little small gimmick from Q. So I will show you some examples.
Sorry, darling, something came off. Well, how's it going?
I've placed through a high security line to the satellite. You can try Bond now.
Good. Are you through to number 10?
Standing by, sir.
You know what I'd like?
Can't imagine.
A moonlight swim.
Number 7, in there. Bond! Bond! Bond, are you there? Here we have a Geiger counter. Useful and unobtrusive. The sweep hand takes the radioactivity count. It's waterproof, of course.
But of course.
With this ultra-sensitive earpiece, you can listen in on the bug. The homing device is compatible with the standard issue radio directional finder in your watch, if you haven't lost it.
That's amazing, Q. It does work. What's that?
Oh, that's the latest liquid crystal TV.
Very handy. Perfect image, Q.
Really, 007. Look, I haven't time for these adolescent antics.
On the air vent.
External elevator pressure. Breaker 5, reset. External LH2 pressure. 25. Retract through access arm. Get back. T-minus 10 seconds. 9. 6. 5.
Bang on time.
4. Come on, quick. 3. 2.
So I hope that you are convinced that always a small little gadget of Q is put into the watch of James Bond. We will now discuss one of these gadgets. It is from the movie Live and Let Die from the year 1973. It's the first movie with Roger Moore as James Bond, and let's take a look at the watch.
I've got your ticket to New York. Q has repaired your wristwatch and some background material on San Monique.
Thank you, Moneypenny.
I'm sure the overburdened British taxpayer will be fascinated to know how the Special Ordnance Section disperses its funds. In future, Commander, allow me to suggest a perfectly adequate watchmaker just down the street. Good God.
You see, by pulling out this button, sir, it turns the watch into a hyper-intensified magnetic field, powerful enough to even deflect the path of a bullet, at long range, or so Q claims.
I feel very tempted to test that theory right now. If you don't mind, Commander, my spoon.
Oh, sorry, sir.
Thank you.
You have seen what the watch is doing. Obviously, James Bond has the watch in his hand. Then he is switching the watch on. Then the watch is able to attract the spoon. The spoon is obviously made of steel or iron. And then the spoon is on the watch, and when he turns the watch off, he can take the spoon off. So it's clear what the watch is. The watch is obviously a very strong electromagnet. So this is again not an interesting question because it's an electromagnet period. He is also saying this, that there is a magnetic field. So this is not an interesting question. Physics is a quantitative science. This means you have to make a quantitative question, then you got a quantitative answer. In order to find a quantitative question, let's look at the following. This is a very expensive watch, a Rolex watch, a very expensive model. So let's first assume that we don't want to open this watch. We have the watch and we have the spoon, and the first thing we can see is the spoon is approximately 1 meter away from the watch. This is what we can guess. Then we will put a wire of copper on the back of the watch in a circle. With a circular wire of copper on the back of the watch. And when we put a current into this wire, then we will get a magnetic field, and we can ask ourselves, how large must the current be to attract the spoon at a distance of 1 meter? This is a quantitative question. So when we put a current in the wire, then there is a magnetic field, and this magnetic field is able to attract the spoon. And we ask ourselves, how large must this current be in order to attract the spoon over a distance of 1 meter? To solve this, we have to look at the forces which act at the spoon. There is, of course, the weight, the gravitation, and in order to attract the spoon, the magnetic attraction must be larger than the gravitation. And you can calculate this, and the result of the calculation is, in order to attract the spoon, we need an electric current in the watch of 4 billion amperes. Wow, this is a big current. We don't ask ourselves what batteries were invented by Q to achieve this. The only thing we ask ourselves is, when you have an electric current, you all know that the wire then heats up. So this watch will create heat during operation. When you switch this watch on, then it will heat up to a temperature of several billion degrees. It doesn't matter if you say centigrade or Kelvin, it's not a big difference. So the watch will be vaporized. In other words, it cannot work. The watch cannot work. It's so simple. Okay, so we have to think a little bit more. We can improve the watch in a sort of a first improvement by winding about 100 turns of wire around an iron core. So we put such 100 turns around an iron core in the watch. So we open the watch, we take everything out, and we put this in a wire coil of 100 turns of copper. This drastically increases the magnetic field. When we now, with this improved watch, calculate the strength of the current, we need 8,000 amperes current only. Well, only 8,000 amps is a very big current. It's a very big current. With this, you can use for a big train like an Intercity Express in Germany, for instance, to move it. So this is a very big current. We don't want to ask ourselves what batteries are needed. Again, the watch would heat up by a couple of thousandths degree centigrade during operation. So it will become liquid and you cannot really operate with this watch. So it's also not working. So what is so difficult when you want to realize this watch? It looked so simple, just an electromagnetic field, just an electromagnet. Well, there are two reasons why this watch is only so difficult to really build. Number one, it's too small. With a larger watch, it might work. We did an experiment at a junkyard in Dortmund. It is shown in this movie. I am sorry, this movie is in German, but you see what's going on.
Aber wie reagiert er auf einen Löffel von 10 Gramm? 3 Meter. 2 Meter. 1 Meter. Erst jetzt gibt der Löffel dem Riesenmagneten nach und fliegt durch die Luft.
So, it was, by the way, it was really a great fun to work there. I was also allowed to do this. It was really a great fun, but it's not so handy, this big magnet, especially when you want to wear it on your arm. This magnet has 50 times the diameter of the watch of James Bond. The magnetic attraction force 1 meter away is not only 50 times larger, but 50 to the 4th power, more than 6 million times larger than the watch of James Bond. So diameter makes a lot for this. And this is the reason why we built the best watch. The best watch is now that we're taking very, very thin wires of copper. Maybe too thin, but very thin wires of copper with 1,800 thin coils of wire. We have a watch of 4 centimeter diameter. This is that much. It should not be larger, otherwise people can see that this is not a real watch. But we make it a little bit thicker so that we can place all the wire coils inside the watch. And the core is not of iron, made of iron, but of some amorphous metal, which a much larger magnetic permeability. This also drastically enhances the magnetic attraction force. This is the ultimate solution. This is the ultimate solution. When we take this ultimate solution, then we only need a circular current of 5 amps in order to attract the spoon over a distance of 1 meter. Of course, the watch will become hot during this. It will heat up to 250 degrees Celsius, and this, well, James Bond must withstand this. He is a top spy, so this does not hurt him. Okay, so why is this watch so difficult to make? Because 5 amps is also quite large, and you need special batteries, and of course the wires are very thin. All this is beyond realization. Now we come to reason number 2. Reason number 2 is the magnetic attraction decreases extremely strongly with distance. At 10 times the distance, the magnetic attraction force is not only reduced by a factor of 10, but by a factor of 10 million. This means when you can attract with an electromagnet a spoon at a distance of 1 centimeter, which is easily possible, then at 10 centimeters distance, you can only attract 1/10,000,000th of a spoon, which is equivalent to the weight of the grain of a piece of sugar. And then at 1 meter distance, you can only attract a 10 millionth of a grain of sugar, which is essentially nothing. This is the reason why we need so much current in order to transport a little bit magnetic field to 1 meter distance. This is a major reason. The magnetic attraction force decreases extremely strongly with the distance. This is the major problem of the watch. And this means that the following would already be possible with the second best watch.
Such a big touch.
Sheer magnetism, Danny.
Well, it's possible because I'm a magnetism man, James Bond is saying, but this is of course wrong. He should have just said the small distance makes this possible. We have tested it. We have done the experiment. It's possible with a current of 100 milliamps and potential of 2 volts, which means a normal battery. When you build with this an electromagnet or a second best magnet, then this is already possible. Okay, but we now know how this watch is working, but we are not finished with this watch. What was the purpose of this watch?
Good God. You see, by pulling out this button, sir, it turns the watch into a hyper-intensified magnetic field, powerful enough to even deflect the path of a bullet, at long range, or so Q claims.
I feel very tempted to test that theory right now.
He wanted to deflect the path of a bullet, he is saying. Of a bullet, of course, made of iron or steel, but this is of course the case. So we ask ourselves, what can he mean with this? And we came to the conclusion that it is meant in this way. Here is a victim, and this victim is shot by a villain. And James Bond is placed perpendicular to the line of fire with this watch, and then he can deflect the bullet with the magnetic field of his watch. And when you see this in a top view, you can ask yourself the following. The larger the distance between the victim and the villain is, the more simple it becomes for James Bond to save the victim, because then he has to deflect the bullet only a little bit, and because of the distance it will not hit the victim. So you can ask yourself, if James Bond is standing in a certain distance from the line of fire, then what must be the minimum distance of the victim from the villain so that James Bond can save the life of the victim? This is a quantitative question. You can calculate this, and when you do this, you come to this curve. This is Bond's distance from the line of fire in this direction. And in this direction, we have the minimum distance which the victim must have from the villain in meters. And what this black line means, you will see in a minute. Think about the following. Maybe James Bond is 80 centimeters away from the line of fire. Just to make this clear to you, this means the line of fire is there. He's almost in the line of fire, but okay, 80 centimeters away from the line of fire. Then you have to go up to this black line, and then you have to go to the side, and you see, then Bond can save the life of the victim when the victim is, well, I would say 4 meters, 3 to 4 meters away from the villain, or larger, or more away. So this is the minimum distance. When James Bond is going 40 centimeters back out of the line of fire to 1.2 meters distance from the line of fire, then when you go up, you come to this point. This is the crossing point with the black line. And then to the side, you can see if he is 1.2 meters away from the line of fire, then he can save the life of the victim only if the victim is 38 meters or more away from the villain. So then it just does not make too much sense to try to save the life of the victim. So then the watch cannot work anymore very effectively. Again, here you can see the distance. It is a very rapid increase with the distance from the line of fire. Okay, so he has to be very close to the line of fire in order to save the life of the victim. But we are still not completely finished with this watch, because there is one tiny thing missing. Look again to the watch.
Commander, allow me to suggest a perfectly adequate watchmaker just down the street. Good.
Have you seen this? This small clip was absolutely correct from the physics point of view. Absolutely correct. You can took this into a textbook. Why? What was so correct? Well, there is a law in physics, the so-called rule of Lenz, and the result from this rule is that a strong electromagnet achieves its magnetic field not instantaneously, but it takes a little bit time for the field to build up. And if we calculate this for the best watch, then we get the result that it takes 3 seconds for the magnetic field to build up. And now take a look. How much time it takes from switching on the watch and moving the spoon.
Commander, allow me to suggest a perfectly adequate watchmaker just down the street. Good.
3 seconds. So the spoon is moving 3 seconds after the watch was switched on. This must be the case. Physics, it's a law of physics that the spoon cannot move in the same moment. It will take 3 seconds. So the laws of physics are totally obeyed in this small clip. Well, this might be interesting from the physics point of view. For James Bond, of course, the situation becomes more difficult. He has not only to be almost in the line of fire to save the life of the victim, he has to switch on his watch 3 seconds before the villain is going to shoot. Okay, but he can manage this. So this watch is then also important in the movie, and James Bond wants to use this watch to escape from a very small tiny island where he has been placed by the villain Mr. Big. Wow, did he really run over crocodiles? Did he run over crocodiles? Well, yes. A stuntman had to run 5 times over the backs of crocodiles.
Define stunt.
As he's about to jump, the crocodiles all do this because they're saying, here comes that guy again. I mean, they'd seen the act twice, and so they're waiting for him to jump again.
Finally, on the afternoon of December the 31st, Roskananga defies death for a 5th time.
This movie was shot 20 years before Jurassic Park. The nice thing of all the older James Bond movies is that everything you see must have been done by stuntmen. Nowadays, of course, you can do this with very sophisticated animations, but at that time it must have been done. And so somebody is really was really running over the back of crocodiles. And we can ask ourselves, how did he do this? How did he do this? In order to understand this, we have to think about the forces which act on James Bond. There is number one, his gravitation. The gravitation would pull him down and would make him sinking in the water. And there are 2 forces acting against the gravitation. Number one is the recoil force. What is the recoil force? A recoil force is this. You put some mass in this direction and you get a recoil into the other direction. And what is here the recoil? Well, when you put your foot into water, you put a little bit mass of the water in the other direction and you get a small recoil in order to move in the other direction, to move up. But this is really the smaller part of the effect. The larger part is the friction force. There is a friction force. When you, for instance, with your hand move through the water, you experience a friction force. You experience a force, and this is a friction force. And this friction force depends on the speed with which you move your hand through the water. And then you can calculate what speed is needed in order to compensate the gravitation, and it turns out 22 kilometers per hour. This is the speed James Bond must have when he is walking over the crocodiles in order not to sink into the water. Well, this friction force depends, of course, also on the area with which you move through the water. And the crocodiles, the purpose of the crocodiles is to enhance the area of the foot by a factor of 10 or so. So you can ask yourself, if there are no crocodiles, is it also possible to run over water? Can you run over water? This is possible, only with the area of your foot, but then you have to be a little bit faster, 100 kilometers per hour. Well, the fastest man on Earth, Usain Bolt, was, while he was doing his world record in the year 2009 in Berlin, he was running with a speed of 45 kilometers per hour. So there is 100 kilometers per hour is not possible. But if you could run with a speed of 100 kilometers per hour, if you can run with a speed of 100 kilometers per hour, then you could run over water. Or you can tune your mass a little bit down. There is one animal who can really, which can really run over water. It's called the Jesus Christ lizard.
With the pond in the way, most lizards wouldn't stand a chance. But this is no ordinary lizard. For years, cinematographers tried to capture its steps with varying success. Witnessed at normal speeds, their fleet-footed water dance leaves nothing but questions in its wake.
Interesting, but this lizard has in common with James Bond, it's only running over water when the lizard is in great danger. It's the same with James Bond, of course. Okay, let's come to the last physics point, to a mirror image. And we will go to the most popular James Bond movie, to the movie Goldfinger. And we will take a look at the first 60 seconds of this movie.
Oh,
Forgive me.
why do you always wear that thing?
I have a slight inferiority complex. Where was I? Oh, yes.
Well, this is very brutal, but we have watched this for scientific reasons. And you see, this is the mirror image of the villain in the eye of the lady. And I will now explain you, when we analyze this image in detail, we will figure out one purpose of the villain and one purpose of the lady. Let's start with the villain. The villain has the stick in the right hand, as you can see. And this is the mirror image we see. You see, there is a problem. You all know that a mirror does exchange left and right. It should look like this. But it doesn't look like this. It looks like this. So we have to explain this first, why right and left is not exchanged. I'm going to offer you now two explanations. Explanation number one. The movie is from the year 1964. What you could do in the year 1964, you could produce such an image by overshadowing. By overshadowing with two scenes. You project with the projector an eye on a wall, and then with the second projector you project the clip from somebody who is moving towards this eye with a stick. And if you produce these two things at the same location, and you then film this simultaneous image, then you have done with overshadowing such an image. This is an explanation. Of course, with this technique, you do not exchange left and right. Nowadays, of course, this would be totally boring. You would take one of these video sampling programs where you can fit two video scenes together. Then you would say, well, this is a mirror image. You can push the button left, right exchange, and that's it. But not in the year 1964. Okay, this is explanation number one. Explanation number two is a little bit more simple. It goes like this. Between this and this scene, he exchanged the stick from the right hand to the left hand. And this must be the correct explanation, because the James Bond movies are telling us the truth. But if this is the explanation, then the villain is particularly dangerous, because he is able to hit you with his both hands. He is not a left-hander or a right-hander. He is a both-hander. So he can hit you with both of his hands with the same strength. And this makes him particularly dangerous. So we figured out that the villain is a very dangerous man. But now we can also get some information about the lady. We will take this as an illustration of an object, here the villain, on a circular shaped mirror. Here we have an object with a certain size, capital G, and a certain distance from the mirror, and we are interested in the size of the object, in the size of the mirror image of the object, I have to say. And this only depends from the focal length of the mirror, and this is given by the radius of curvature of the surface of the mirror, R. And so if you have this, you have to take the simple laws of geometrical optics. You have here the object. The object has a size of 1.8 meters. How can we know this? Well, the attacker was had approximately the same size as James Bond, and James Bond was 1.83 meters. So 1.8 meters is a good guess. He is 2 meters away from the mirror, from the eye of the lady, which we can also guess in a very good way. Then the radius of curvature of an eye is approximately of a human 9 millimeters. 9 millimeters. It's an average value. And of course, we are interested in the size of the mirror image. This is what we want to calculate. And when we do this, it turns out the size of the mirror image is supposed to be 4 millimeters. This is the result of the calculation. Well, then you must know we have very motivated students at TU Dortmund University. They were just saying, let's try this, let's do the experiment. So you can see here the eye of Mrs. Voronyuk, Katarina Voronyuk. Katarina Voronyuk, at that time, she was a student. Now she is a teacher at Dortmund Gymnasium for physics and mathematics. This is the eye of Katarina Voronyuk. And she was attacked by Frank Holmes, also a physics student at that time. Well, attacked, they just wanted to make it look like in the movie by Frank Holmes. Frank Holmes has a size of 1.8 meter, exactly as in the movie, and he is 2 meters away from Mrs. Voronyuk. And when we measure the size of the mirror image, then we get 4 millimeters. Well, this is physics. We had a theory. The theory value was 4 millimeters. We do the experiment, and it exactly matches. I'm always saying in physics, the only science where the predictions really came true. Yeah, but this does not solve our problem, but then something is still wrong. We did not want to calculate the size of Mr. Holmes in the eye of Mrs. Voronyuk. In the movie it looked like this. Half of the size of the attacker fits completely into the eye of the lady. This means the size of the mirror image in the movie is 2.8 centimeters. 2.8 centimeters rather than 4 millimeters. Okay, this means that something must be still wrong. Maybe the size of the attacker is wrong. Yes, everything fits completely if the attacker has a size of 12.5 meters. Well, you may laugh, but frankly speaking, my theory colleagues, for them, this would be the solution. Since I'm an experimentalist, I would say no, the attacker did not have the size of a 4-story building. Something else must be wrong. Maybe the distance of the attacker was wrong. The 2 meters was only a rough guess from us. And again, you can see our 2 students, and you see now Mr. Holmes, half of Mr. Holmes is totally filling the eye of Mrs. Voronyuk. So the size of the image is 2.8 centimeters, as we have seen it in the movie. Well, yes, but you must know, Mr. Holmes is at 30 centimeters distance from Mrs. Voronyuk. If this were true, then between Mrs. Voronyuk and Mr. Holmes, there must be James Bond placed. And this would mean that he did not need such a mirror image, because he would recognize the breath of the attacker in his neck because he is so close. This could also not be true. So the only thing which is possible is that the curvature of the eye is somehow special, the eye of the lady. And everything fits together if this curvature is 6.3 centimeters. This means 9 millimeter curvature is the curvature of a 2-cent coin. So a 2-cent coin has approximately the curvature of the eye of a human. And 6.3 centimeters curvature is this. It's a 7 times weaker curvature of the eye of the lady. So what we figured out is that the eye of the lady is very weakly curved. The curvature is very weak. And this means also that the curvature of the second eye should also be very weak. Why should the two eyes have developed in a different way? So the curvature of the eyes of the lady is very weak. You cannot compensate this with a contact lens. In other words, we figured out that this lady cannot see anything. She's blind. She may have recognized James Bond by his voice, or she smelled him, but she definitely could not see him. So we figured this out, and this is a very important information about the lady, which was just commented by James Bond in a special way.
Shocking. Positively shocking.
Of course, he's not talking about the lady. He means a sad situation where they are all in. Okay, let's come to the end. Let's come to the question why James Bond is taking his vodka martinis shaken, not stirred. But first, let us convince that he is just doing it.
Can I do something for you, Mr. Bond?
Just a drink. A martini, shaken, not stirred.
Yes, sir.
The lady will have a Bacardi on the rocks.
For the gentleman, vodka martini, shaken, not stirred.
Touche.
Miss Kennedy, would you get me a medium dry vodka martini?
What?
Shaken, not stirred.
Cut.
And what words do you live by?
Trick is to quit while you're still here.
That's one trick I've never learned. Perhaps you'll show me how it's done. Vodka martini, shaken, not stirred. And for you?
The same.
You have seen it. And Daniel Craig is also doing it in the 24th movie Spectre. He ordered a vodka martini, shaken, not stirred. So why is James Bond doing it? People have investigated this already, and this was already investigated by Canadian scientists. Shaken, not stirred, bioanalytical study of the antioxidant activities of martinis. This study was published in a very prestigious journal, and the final conclusion of these people is 007's profound state of health may be due, at least in part, to compliant bartenders. There it is mentioned it's done because of health reasons, because the shake vodka martini is healthier than the stirred one. Well, in order to prove this, you must give some proof that James Bond wants to live very healthy. And this is definitely not the case. There is no indication that he is really taking care of his health so that he wants to eat very healthy food or something like this. On the contrary, James Bond is always eating not very healthy things. So there is really no proof that he is really taking care about his health. So I did not buy this explanation, and I tried to figure out another one. And I have to warn you, this is my explanation, it's a physics explanation. If this is a real explanation you can judge by yourself. Of course, as a physicist, I look to the molecules of a vodka martini. A vodka martini consists of two parts of molecules. On one hand, you have rather large, so-called aromatic, ring-shaped molecules. And those molecules are responsible for the taste of a drink, these large molecules. And the small molecules, the alcohol molecules, alcohol, ethanol, a very small, tiny, compact molecule, they are responsible for, well, for the kick. So a vodka martini consists of two parts of molecules, large ones responsible for the taste, smaller ones responsible for the fun. Okay, what is happening with mixture of large and small particles? Well, if you eat this, you know probably what you have when you have a mixture of large and small particles. It's called the Hazelnut effect will happen there. This means the following. If you have heavy green balls and light black balls here in the box, and the heavy green balls are underneath the light black balls, and if you shake this box, then for some magic reason, at the end, the heavy large balls are on top and the light small balls are on the bottom. This is a very complicated matter of so-called granular matter, which is very difficult to explain. Here in the computer animation, for instance, you can see that sometimes you have a small hole here. This means a small particle can go down, but you never have a large hole so that the big particles can never go down. But if only the small particles can go down, this means for the big particles they have to go up. Well, this is theory. Let's do the experiment. Let's mix a vodka martini, a James Bond vodka martini or a model vodka martini. This is our glass, and these are the big molecules responsible for the taste. And now I put the small molecules on top, responsible for the alcohol. So these are the small molecules. So we have now a mixture of large and small molecules, the same as in a vodka martini. And when I shake now this, you can see that all the big molecules are going to the top. I think it's clearly visible that all the big molecules are now on the top. Well, what this has to do with James Bond, you will see in a minute. Here you'll see again the experiment a second time. You can see this. Here again, what I showed you a minute ago in a movie, where you also can see that the big molecules are, the big balls are going to the top. Okay, this means in a stirred vodka martini, all the big and the small molecules are equally distributed. In a shaked vodka martini, the molecules which are responsible for the taste are all on the top. And now we just have to think about for whom we are doing this. We are doing this for James Bond. Obviously, James Bond knows when he is ordering his drink that he will not have the time to fully drink the vodka martini. He can just take one mouthful. And this one mouthful, the taste of this drink should be maximized. It should have the best taste. And so all the taste was shaked to the top of the liquid. This is my explanation. He is doing it because he is interested in the good taste of the vodka martini. And in contrast to the health theory, my theory can be proven.
Too many free radicals, that's your problem.
Free radicals, sir?
Yeah, they're toxins that destroy the body and the brain, caused by eating too much red meat and white bread and too many dry martinis.
Then I shall cut out the white bread, sir.
Then I shall cut out the white bread, sir. Of course, this is the proof that he is interested in the good taste of the things he is drinking and eating. Okay, so I'm almost at the end. Here you can see the 41 students which work together with my colleague Joachim Stolze from the theory division and me. We made a seminar 13 years ago with the students in order to write a book about the physics of James Bond. You can buy this book. This is the German version of the book, which has been updated recently, so that it also contains now a lot of stunts of Daniel Craig. And this book is also published now in an English version, Shaken Not Stirred, James Bond in the Spotlight of Physics, as you can see here. It is even also published in a version in Portuguese so far, but these are the only languages where the book has been published so far. You see the references, you have seen images from licensed James Bond pages, you have seen from the original DVDs the movie scenes, and I'm also thankful for Frank Priest. He helped me by selecting the different movie clips from the James Bond DVDs. I'm making PR for this book because if you buy this book, you do not support poor professors at our university. You do support our students. So all the money which is collected by selling this book is directly going to our students in terms of stipends or other things. So when you buy this book, you do not only have a very good physics book, you also support our students at TU Dortmund University, our physics students. And we have a lot of very, very good physics students. It's worth doing it. So this is the reason why I am making PR for this book in a very aggressive way. Okay. Well, we are close to the 25th James Bond, but the 25th James Bond has been postponed a lot of times, and it is now scheduled for for the 2nd of April 2021. Well, probably it will be again postponed. One has to be careful. One has to change, otherwise the photos in the advertisement if this postponing is going on and on. But we have 24 movies so far, 24 James Bond movies, and at the end we can make a small James Bond statistics. In the 24 movies, Bond ordered 28 vodka martinis and visited 37 different countries. 13 times he was told that he will die. We have 60 Bond girls so far, and you can divide them into different classes. Women whispered 16 times "Oh James," and the next number was really investigated very, very carefully by us. We looked at every scene, we discussed it, so that it is absolutely clear, it is crystal clear, that James Bond had in the 24 movies, in all 24 movies so far. So he had, in all movies, in all 24 movies, 84 times sex. Of that, 26 times in, at, under, or on the water, 19 times in hotel rooms, 2 times in an apartment at London, 40 times at her, 1 time at somebody else's place, 3 times in a train, 2 times in a shed, 2 times in the woods, 2 times in a nomadic tent, 2 times in a hospital, 2 times in an airplane, 2 times in a water plane, 1 time in a submarine, 1 time in a car, 1 time in a motorized iceberg, 1 time under the shower, and in the movie Moonraker, 1 time in a space shuttle, and I'm going to show this to you at the end.
Colonel Scott reports picking up 2 survivors from the space station, a tall man and a short blonde woman.
Right. Okay. Dr. Goodhead reported their position 20 minutes ago. They're just coming into range of our tracking ship in the Pacific Ocean. We should have audio-visual within a few minutes from the remote onboard TV monitors.
Houston calling Dr. Goodhead. Houston calling. Confirm your position.
As this is the first joint venture between our two countries, I'm having it patched directly to the White House and Buckingham Palace.
Well, I'm sure Her Majesty will be fascinated.
We have audiovisual.
Ah, at last.
My God, what's Bond doing?
I think he's attempting re-entry, sir.
James,
I think it may be time to go home.
take me around the world one more time.
Why not?
Where are you? Why do you hide? Where is that moonlight train that leads to?
Thank you very much for your attention. Thank you very much that you followed me about the physics of James Bond. Thanks a lot.